Greetings and welcome to the Chemistry 223 Determination of an Unknown Chloride Lab. This is kind of a cool lab because even though at Mount Hood Community College we oftentimes face, shall we say, considerable financial pressures, which means i.e. we don't have a lot of money, I feel that Mount Hood Community College is able to compete with the better schools of chemistry in this lab because this lab involves what's called a titration. And the techniques used for titrations aren't too sophisticated, too crazy. So we can do as good of a job in this lab at Mount Hood Community College as you can in the other bigger schools, which is kind of a cool thing. So without further ado, let's see exactly what's up with the Unknown Chloride Lab and titrations. The goal is to find the percent chloride in an unknown compound. So all we know about our compound is that it has a source of chloride, and we need to figure out the percent chloride, i.e. in 100 grams of this compound, how many grams of it are just chloride. And what we're going to do is use the idea that if you have a chloride, all right, most of the time chloride is pretty soluble, but when a chloride is with silver, mercury, or lead, one of the exceptions from the net ionics lab we did earlier, you can actually form an insoluble compound, silver chloride. So we're going to use a silver plus ion source, which will be AgNO3, silver nitrate. We'll add it to the chloride and essentially create a type of precipitation reaction. Precipitation, once again, means that something solid forms. We can use this information then to find how much chloride was in the original compound if we have a good value for the silver nitrate. So in part A, the goal is just to find a really good value for the molarity, which gets the capital M symbol, of the silver nitrate solution. All right, the silver nitrate is what we're going to use to find the chloride, and if we have a good value of silver nitrate's molarity, we'll be able to find a good value of the chloride, again using this titration idea. In part B, we're going to use our good value of molarity for the silver nitrate solution to actually find the percent chloride of an unknown, and it's pretty cool. Now, in both part A and part B, we're going to do multiple trials. And if you have multiple trials, you can. It's nice to know sometimes if at the very least your precision is high. And what that means, precision is like how close your measurements are to each other. And parts per thousand we're introducing here is something that chemists use a lot of times to find out how precise your measurements are, like how close they are to each other. A parts per thousand analysis is just a little cheesy kind of math thing to do, and the result will be a number. And the smaller the number, the smaller your parts per thousand, the higher your precision. So if you have a small parts per thousand, your measurements are really close to each other. On the other hand, if you have a really large parts per thousand, that just means your measurements are quite a ways from each other. And usually small parts per thousand means that you were doing a good job. You were paying attention to the details and you got them really close to each other. A lot of times high parts per thousand means that you weren't paying attention and the data was all over the place. And it can mean also that there was something else going on with the experiment, but a lot of times, all right, this is a good thing. So small parts per thousand at the very least allows you to pat yourself on the back saying, hey, you did a good job taking the measurements. Now, this doesn't say anything about the accuracy, all right? So we could have really good parts per thousand precision with a really bad percent chloride. We wouldn't know that from parts per thousand, but it at least does make us know that we tried really hard then to make our measurements as good as possible. So parts per thousand is just a way to make sure that you're kind of at least trying to do a good job. There might be other variables keeping you from a good accuracy value, but at least it lets you know you're doing a good job. Titration is this powerful technique, and again, I feel that at Mount Hood we can keep up with the best schools and stuff through it. If you're doing a titration, you'll use something like the little picture in the lower left, and you can see there's like a kind of a tall glass thing right there. That's called a burette, and a burette is one way to add chemical, and if there's like little graduations on there in terms of milliliters, so it's a very good way to get accurate amounts of volume in. And there's lots of different techniques here and words, and I want to go through them. So this titration is just something where you're going to use a burette. You basically are adding one solution into another. And there is always going to be a color change associated with a point where you get to what's called the equivalence point. The color change comes from another chemical called an indicator. Our indicator in this particular experiment is potassium chromate, and it makes kind of a cool color when you get to this equivalence point. And I'll show you in the video later how that works out. Equivalence point is the moneymaker, though. Equivalence point means that the moles of what you're adding equal the moles of what you started with. Now in part A, we're going to start with so many moles of sodium chloride. So that's going to be what we're going to find is equal. So the equivalence point in part A mean that the moles of sodium chloride equal the moles of silver nitrate that we've added. In part B, we don't know the source of chloride, but we can still say that at the equivalence point, the moles of chloride equal the moles of silver nitrate added. So you can see if the moles are equal, then we can start to do lots of different transformations and stuff like that, which is cool. Volumes in a burette can be read to the hundredth of a milliliter, so 0.01 milliliters. So if you do this lab in the actual laboratory setting, make sure that your measurements always go to a hundredth of a milliliter. In addition to using a burette, we're also going to use a new type of balance for this particular experiment called an analytical balance. Analytical balances go out to a 10,000th of a gram. So they go out to 0.0001 grams. It's pretty amazing. They're much more sensitive than the top loading balances that we use most of the time in our chemistry labs at Mount Hood. The analytical balance just gives us one more power of 10. So in this lab, where significant figures, again, are really important, we're going to end up with balance measurements out to the 10,000th of a gram and volumes that can be read to a hundredth of a milliliter, 0.01. We're going to get some pretty good sig figs out of these. This parts per thousand thing is pretty chill. There's a handout at mhchem.org/ppt that will go through some more details, but I wanted to talk here a little bit about it. First of all, it measures the precision of your measurements. It doesn't measure anything about accuracy. And again, precision just means that your values were fairly close to each other, all right? And that's usually a sign that you were paying attention in lab, all right? It doesn't have anything to do with accuracy. So our values could be really far off, and we wouldn't know that without having some kind of external verification from it. But we can at least say that the values are good. This table in the lower left is something from the lecture notes that shows a series of boiling points for a compound. And you can see that this scientist took 4 trials, and there's the 4 boiling point values that they got. And you can see that they're all 11 point something. So the boiling point is around 11 something. But we can do a better job. So when a scientist has multiple sets of data, the first thing they do is they find the average. Now, how this 11.19 number came around is someone added up 11.23 plus 11.09 plus 11.27 plus 11.16, and they got a number. And to find the average, you take the sum of all that stuff and divide by the number of trials. So you would take the big number and divide by 4 in this case, because we have 4 trials. That's where the 11.19 number came from. And I encourage you to try this on your own, because you're going to do a parts per thousand here in a little bit, and it's pretty easy. So that's the average. We would say that of the 4 values, it looks like the average boiling point would be 11.19 degrees Celsius. But if you want a parts per thousand, it's pretty chill. What you do is you take the positive difference between the individual values and the average. So 11.23 minus 11.19, that's where the 0.04 came from. And you can see that that's a positive number. All right, no big deal. But the second one, 11.09 minus 11.19, initially comes out to be a negative 0.10. When it comes to deviations, you want to use an absolute value. And what that means, just make your negative numbers positive. All deviations will be positive numbers. So even though 11.09 minus 11.19 was initially negative, we made it positive. And that's what you want to do for all deviations. No negative deviations, okay? So the next one, 11.27 minus 11.19, comes out to be 0.08, no problem. The next one, 11.16 minus 11.19, initially is negative 0.03, but again, we made it positive. All deviations are positive. Once you have the deviations, you need to find the average deviation. And to find that, you add up the 4, in this case, deviations. So 0.04 plus 0.10 plus 0.08 plus 0.03. Add them up, divide by 4, because there's 4 trials. That's where 0.06 came from. So you can see that average was just all the individual boiling points added together, divided by 4. Average deviation is just adding all the deviations together and dividing by 4. Finally, parts per thousand, PPT, is average deviation divided by average times 1,000. So in this example, you take average deviation 0.06, divide it by the average 11.19 times 1,000. Parts per thousand here is 5. A parts per thousand that's under 30, I always consider to be exceptional, which means you were paying attention to your experiment. So this person, when they did their boiling points, they were paying attention to their stuff, all right? If you get a parts per thousand that's larger, then it maybe means that there's a little problems with the experiment. Again, look to the handout at mhchem.org/ppt. It's also in the companion for another example of how parts per thousand works. It's something we'll do off and on from here all the way into Chem 223, so it's a good idea to know how it works. In part A of this lab, the goal is to find the best silver nitrate molarity value possible. All right, the stockroom, the people that make the chemicals, will a lot of times say, well, our silver nitrate is about, say, 0.05 moles per liter. But we might want to know to better detail what that value is to more significant figures. And it's actually pretty easy to do. So this is the symbol for silver nitrate. That's moles per liter. That means moles of silver nitrate per liter of solution. And so in this next part here, if you take the grams of silver chloride that you start with, and it'll be in this lab a number that's about 0.1 grams, you can turn it into moles, which is the next step. The question mark there is the molar mass. So you'd add up a sodium plus a chlorine from the periodic table to get the molar mass. Sodium chloride is roughly 58 grams per mole. You want to find a better value, more sig figs to put in there. But this step just allows you to go from grams sodium chloride to moles of sodium chloride. Then, as we saw a second ago, chloride and silver ions are 1-to-1, like one silver needs one chloride. So for part A, that means that one silver nitrate needs one sodium chloride, or better yet, in chemistry speak, 1 mole of silver nitrate is needed to react with 1 mole sodium chloride. So we're turning the moles of sodium chloride that we start with, which is this part, into moles of silver nitrate that were needed. That's what the 1-to-1 ratio means, all right? This is an example of the grams to moles part of a conversion, where you first go grams to moles, and then it's a 1-to-1 stoichiometry, so you're turning it into moles of silver nitrate. So this whole part then, getting to right here, has been just to get to moles of silver nitrate. And you want to essentially divide by the liters of silver nitrate used. And in this lab, it's going to take roughly 20 to 40 milliliters, maybe a little bit more, maybe a little bit less. You want to turn it into liters. The way this is set up, if you have milliliters in the bottom, then you would multiply by 1,000 to get it into liters. If you already took the milliliters and turned it into liters, then you can ignore that 10 to the third right there. That's just a conversion to get it out. But anyway, when all is said and done, you're going to get a good value for the silver nitrate. You'll have 3 silver nitrate concentration values because you're going to have 3 different trials you're going to do. You will find the average of the 3 and then the parts per thousand, just like we did earlier. And the average silver nitrate concentration, the average silver nitrate moles per liter, is an important number. That's what we're going to use in part B in the next part. So these 3 trials, you'll add them up, divide by 3 to find the average. That'll be used in part B, but you'll also find parts per thousand to see how you're doing, stuff like that. No problem. I think this little equation here will help out a lot. The molar mass of sodium chloride will be the same for all trials. This number, the grams of sodium chloride, will change, and this number, the milliliters of silver nitrate, will change. But all the rest of it is a constant, and the numbers, the final answer you get, they should come out to be pretty much the same. They'll be a little bit different, but pretty close to each other. In part B, the goal is to find the best percent chloride value for your unknown sample. And this kind of generic equation here is the way that you can use to find the percent chloride. Now, percent chloride is equal to the grams of chloride in your sample divided by the grams of sample times 100%. And when you start these experiments, you automatically know how many grams of unknown you do. This is something you would weigh out. It's a number, I believe, between 0.10 and 0.12 grams. So that number is going to go right there at the question mark. Now, you also know how many milliliters of silver nitrate it took to get to that endpoint, to the equivalence point. So if you take the milliliters and you turn it into liters, which means divide by 1,000, you'll have the liters. Then you can multiply by the average silver nitrate from part A. So in part A, the average of your 3 trials, that number is going to be used in part B. It's going to go right there. And then just like we saw in the last one, 1 mole of silver reacts with 1 mole of chloride. Unlike the last one, we don't know if this is sodium chloride or something else, so we just have to put Cl-. But we do know that every mole of chloride is 35.453 grams. That number is not magical. It comes from the periodic table for the number under Cl, number 17. So this whole part right here, starting with the milliliters and getting to this part, that's all the grams of chloride. That's what that whole part is. And if you take that grams of chloride and essentially divide by the grams of sample and multiply by 100%, that's going to give you the percent chloride values. So just like last time, you're going to have 3 sets of data. You're going to have 3 separate percent chloride values. You'll then add them up, divide by 3 to find the average percent chloride. That is kind of the holy grail, kind of the cool thing you're after in this lab. You'll also find parts per thousand just to see how you're doing and stuff like that. Now, watch significant figures when you're doing these. All right, both the percent chloride and the earlier AgNO3 values. Make sure you watch your sig figs. It's just multiplying and dividing, so smallest number of sig figs rules. And finally, this is probably not as obvious since we're not doing this lab. Silver nitrate, if left on your fingers and not washed off, will leave a kind of a spot. All right, and so if you do get silver nitrate on your hands and you just rinse with water, it comes off readily, no problem. Or if you better yet use gloves in the first place, you'll be fine. But anyway, that's what the little joke is all about and stuff like that. So the superhero there, he has gloves on. And anyway, my sense of humor leaves a lot to be desired. I apologize. So in this lab, again, the goal of part A, find the best average silver nitrate concentration, the best silver nitrate molarity, moles per liter. And then in part B, you'll use the average silver nitrate value from part A to find the best average percent chloride value from your 3 sets of data. All right. Report parts per thousand for parts A and part B. Don't average anything in part A until you get to the 3 molarity values. All right. Then you can average those, find parts per thousand. And the same for part B. Don't average anything until you get those 3% chloride values. Then you can average in parts per thousand and you're good to go. If you average things before, you won't be able to do parts per thousand and you'll have a point penalty. So make sure you don't average anything in part A until you have the molarities. Don't average anything in part B until you have the percentages. Okay, at this point, I think it's time for a video. Good luck with your studying. Good luck.